Class is better because this morning everyone is fresh compared to Tuesday one. Right. Not fresh. So we have a very slow start, probably slightly slower. I will increase the pace as it goes. So I was exploring you what is MEMS basically last lecture. I started giving some history and probably I was saying miniaturization is one important aspect which has led to this MEMS technology. One of the interesting thing is we try to consume less power. That's a good thing about miniaturization. Not only that, what makes MEMS? What is the demand behind this? Just some points before I go to more detailed technical aspects. If you look into the market, as I say, it's very important to know what the current market interest is about. There is a need for intelligent systems, example smartphones, or robust. It's a very strong devices which have good strength, and also multifunctional. That means once again, the smartphone is a good example which all of us can actually really realize. A single same chip wants to do several activities. You want to combine them together, whether it is a sensing or actuation. So there's a need for such things are very now a rapid request in the market now. So that's a big driving force, and also low cost industrial products. Okay, so how can we make some low cost? Okay, if you go for a shop when you have a handmade item, it's quite it's always expensive. Why? Because the person has to do one by one. Yeah. At the same time, if it is a machine made, they say machine cutting gold. You don't want to pay any. Have you seen this in the gold shops? Not in the Pokong, probably in some other shops. They say that if they don't have making charges for the gold, if you do buy for the machine, if it is done by machine. But if it is done by a human, they will ask for the making charges. Why? It's obviously the one which is done by a human is more expensive because he does one by one, or it is something has to be structured. Okay, so when we do many things together, automated stuff, that we call it as batch fabrication. Okay, we do in batches. So that is actually possible when we go for miniaturization. Say for example, one single silicon wafer can actually build hundreds of transistors or hundreds of MEMS chip. So these are all some driving forces for this MEMS to lead in the market. Okay. I give this example before I go more details. Just a thought for you all guys. This is a mosquito, right? Yeah. So probably there is another picture, cartoon of it. A drop of blood is there in this. So mosquito is so tiny, yeah, and its straw is still more tiny, right? But it can just sit on our skin. We don't realize that much. It can put its beak. Can you feel that time when it pinches? We don't feel it. Okay, we feel itchy after the mosquito flies because it leaves some enzyme, so we feel itchy. But when it pierces in, we don't feel it. Okay, but it takes some amount of blood. Okay, that means how it is. It has to suck. So that means there is a pump inside the mosquito, and there is a small microfluidic channel, and it actually consumes a small amount of fluid and runs away. You don't realize it also. You don't feel it also. It is so tiny big, it's able to enter inside. Okay? So if you zoom it in microscope, then whatever the straw or the mouth or beak of the mosquito is just very tiny stuff. A mosquito can do this. Why don't humans we can do something like that? Okay? So a natural example we have of miniaturization is simple I want to tell you here. You can see a whole lot of mechanism is happening here. Okay, there is sort of known amount of fluid is exactly consumed, and the size of the microfluid channel, the so-called beak, is so tiny. Things are happening. Okay, so why don't we think of miniaturization? That's what all about. Okay, we learn from nature. Okay, some serious points. What is the need for miniaturization? Okay, quickly I'll go on this. Why do we think we need? Okay, one is the market. I said that's the another. The another thing is technical reasons. Why we why we need smaller things. Okay, let's start with the first one. Smaller systems tend to move more quickly to low mechanical inertia. What is mean by inertia? Some physics and chemistry we will have here and there. Okay, inertia is opposite to the force. Okay, so that means it has low inertia. That means it can move quickly. The smaller system can move quickly. That's obvious, right? Elephant takes more time to walk rather than a rabbit or some other animal. It's faster. Yeah. It's thus ideal for precise movements and rapid actuation. Okay. So in many of the industrial applications, mechatronics students may know, there may be need of very precise movement of some automation system. For example, you want to cut a thing which is exactly should be 2 millimeters. Then there should be a precise movement of that particular movement of some objects. So this can be achieved only, if we have some sophisticated, that can be achieved by this. Then encounters less thermal distortion and mechanical vibration due to low mass. I have asked this question 3 years ago in the exam paper. Okay, let's see what kind of question I asked this on this. I asked the students, how do you think that the smaller or micro devices or miniaturized devices will experience less mechanical vibrations or noise due to mechanical vibrations? Before I give the actual answers, I want to hear from someone what you think about. What is the question? Okay, the question is, the statement here says, when you make things smaller, okay, you will have less noise due to mechanical vibration or less noise due to thermal distortion. Okay, let's thermal distortion maybe is hard to think. Let's only concentrate on how the small devices will have less noise due to mechanical vibration. Okay, let's take our automobile car. Say, for example, the front, what do you call that? The front piece which covers in customer car.
Bumper.
Bumper. Okay, bumper. Say 2 screws are gone out there. Okay, now you're driving. Okay, that's a noise that is caused by some mechanical structure. Okay, that's a noise. That noise can actually, it's a noise we hear, but it can also translate to some electrical signals noise. In some way it can transduce. Achieve that. I'm now saying that is less in case of micro devices. Why do you think so? Any good answers?
I mean, because like the first statement, it says that when objects tend to move very fast, it also tend to move very slow. I mean, it can accelerate quickly because of inertia.
Okay, new scientist born here. I don't understand.
I mean, because it's like, because you're easy to fast, right? I mean, if there's a force applied, then there's a very fast movement. So to decelerate it also.
Thanks for your imagination, but that's not expected. Any other answers? But good, he's thinking. That's nice. Anybody else? I want an answer from mechatronics. Many answers I want from mechatronics because these things you should be knowing. Okay. ECSE, I know they cannot find out, but still very good. ECSE. We are all the same team. Okay, good. Okay, the problem, okay, let's see this. Every object, any structure here, table, chair, this one, or even our human body, every structure has a fundamental resonant frequency. Okay? In your school time in physics, you might have studied when the soldiers walk on the bridge. When they walk in the same, if they march in the same frequency of the bridge frequency, okay, say the bridge frequency is 6 Hertz, and if these fellows are marching at the same frequency of 6 Hertz, the bridge can vibrate along with these soldiers and it can break. This we call as resonance between two structures. Right? Now, how, keeping this in mind, this example, when we come to the smaller structures, even this chair, this has some fundamental frequency. If I try to shake, vibrate this in that frequency, it will have maximum amplitude of movement. That's called resonance frequency. Okay? So when I go to the smaller structures, say a small cantilever beam, which is of micron size, like 100 microns, very smaller ones. The mass of this structure, okay, is going to be very small. Yeah, the mass is very small. There is a formula. The fundamental frequency is square root of k by m. Where m is the mass, m is an elastic constant of that material. Okay, let's not worry about this. This is a constant. It's not going to vary for a material. It's going to be stay like this. Yeah, but mass can vary based on the size of that material. If size is large, mass is small. Yeah. So what happens when we have tiny structures? The mass is in the denominator here. So what will happen is the frequency, the resonant frequency of the smaller structures are in the order of, could be higher. It will be a high number. Yeah. Now normally the mechanical noises what we have in our day-to-day life, they could be in the order of a few hertz. Okay, do you understand what I'm trying to say? The noise produced by the same personal car, the bumper one, you can hear it. You can even see that vibration. So that means in every second it may be vibrating like say 10 times. So the frequency is actually quite bigger, right? You can see it. So imagine that its vibration is a rotation of a fan. Can you count when it is rotating? Cannot, because the frequency is so fast. Yeah. Now if the frequency is so fast, okay, it's actually beyond any mechanical vibrations that can happen in the actual world. Okay, so the actual world vibrations may not affect the smaller dimensions that much. Do you understand this point? What I'm trying to say here? The vibrations of the macro world, what we have, the noises produced, these frequencies are a low frequency usually. Okay, the noise, the mechanical vibrations. But when we go to the smaller dimensions, the resonant frequencies of those structures are quite high. You understand what I'm trying to say? Could be, say, this structure could have a resonant frequency of 1 megahertz. 1 megahertz means 1 into 10 power 6 hertz. That means in 1 minute of time, it's around 1 into 10 power 6 oscillations can happen. That's the meaning. But the vibrations, what this check, suppose I keep the macro device here and I'm going to shake this, probably this oscillation is a few hertz. So these vibrations, the transition from this vibration to the micro device is not that efficient because these two frequencies are so different. So mechanical vibrations have less impact on microstructures. But if this also vibrates at the same frequency, and that is also, then you have a different issue. But generally, the normal noises are of very low frequency, but the micro devices will have higher resonance frequencies. Okay? Anyone didn't understand this? What I'm trying to say? Did everyone got this? This is lot of some different than your ECSE subjects. The mode of thinking. Huh? Is it okay? You got this? What I'm trying to say? Yeah. So similarly, even the thermal expansions are also not again when you heat certain materials, it expands or contracts. Okay, so this expansion or contraction is not that frequent for smaller dimensions. So we can actually experience some low. That's what now you read the line. Mechanical vibration due to low mass. So since the mass is low, your mechanical vibrations is low. Yeah, because mass is sitting at the denominator. This one is a very famous equation. Electronics, have you seen this before? Root of k by m. Even in fact, our ECSE students would have seen this somewhere in the first year. Okay. Always, even in computer system, I used to say, have you seen this for loop? This one, they'll say silently. So I understand. So better not to ask. All say. Okay. Third point: miniature devices are particularly suited for biomedical and aerospace applications. Yes. Sometimes in the aerospace applications, one example I want to hint here. When they send a satellite, they also send some, they call as a payload. So the payload has instruments that actually can repair the satellite and so on. So that system is quite a heavy one. But these days now the payloads can be made miniaturized and actually it reduces the size and weight which you have to launch. So there's quite a lot of opportunities there. And also have high dimensional stability. As I said, due to low thermal expansion. That means the expansion is not that frequent, and it can have the dimension, the stability of the dimensions, because it's already too small, so you will have more higher stability there. Ready mass production in batches, less material requirements, obviously smaller ones, so these are some tiny points. Okay. So how do we miniaturize now? That's the next question. So I was talking about the need, how the market was, and then I was saying how the need for miniaturization of the demand. Then now I'm coming to a point, how can we make this? So how can we make it? There are two approaches, and this particular picture, this was a Nobel Prize winner. Everybody puts this picture in their slides when they talk about nanotechnology, so I also put here. Okay. What he said that, he said that there is quite a lot of room under something blah 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 blah. So that became like everybody started citing it. Oh, this picture is saying this. So what he said is, we can actually build from molecule to molecule and construct it and make devices. That we call it as bottom-up approach. Bottom-up approach means you build. It's like your Lego game, Lego building thing. Right? Those things what you try to put one over other, and you try to make a new structure. So imagine now you put one molecule on another molecule, but basically everything is molecules here. Yeah, this plastic is full of molecules. It's just they are placed together and they form a solid. Yeah, so you put one other, then you can make. He says tiny devices. It's possible. The another way is a top-down approach. Any idea what could be that? Top-down approach. Deconstruct. So when I said that bottom-up approach is you build. Top-down approach means you remove unnecessary things. Yeah. So, for example, making a statue, a sculpture making a statue. So he brings a big block of stone, then he starts removing the unwanted thing and makes the shape of that, whatever the idol he wants to make. So my top-down approach is more of removal of unwanted materials or micro-machining to realize the miniaturized structures. So these are the two approaches people usually do, and probably in place, both are actually widely used for both nano dimensions as well as micro dimensions. Yeah. Right. Some differences between. There is a lot of differences, but I just want to highlight before we pass on to some next topic. So now we have an idea. I was telling about MEMS chips have sensors and actuators, whereas the traditional one, 2D microelectronics, what you know is the chips what you are using in the labs till date. So what is some differences between these two? Okay, 2 marks question. So let's say, the first one is primarily microelectronics or just 2-dimensional structures. If you see your PCB is just 2-dimensional, right? It's just 2-dimensional. But whereas in our case we can have gears, motors, it could be 3-dimensional. Micro mostly it is stationary structures. Here you can move components. Let's so I allow you to read yourself. It's quite simple, but something I like to pick up. Okay, even the third point is good. Transmit electricity for specific electricity function. So if you take our normal 2D electronics, we only have input is electricity, output is also electricity. But whereas in this case, input could be anything, output could be anything. But there is definitely some electricity there anyway. Yeah, so it could be biological, chemical, and so on. So this actually, I would say, I will admit that this slide is slightly older one. For example, from 2005, people are saying the same thing, still adopting it. They said that manufacturing techniques is not that developed, but now, at the present 2017, the manufacturing techniques are on top. That's why we are getting a lot of new devices. So going to applications. So this is actually, I finished last class, highlights of all the MEMS technology. That you see, I mean, majority of success happened in automotive. The numerous sensors and also in biomedical applications. Just the key things. One of the main success was the safety, which you saw in the video as well. The accelerometer that can actually open up an airbag. Also, several wherever you need to measure pressure or humidity or even the fuel flow, every places, the MEMS sensors have been used a lot. So almost now, if you don't have all these things, and then it is just 4 wheels and the engine, right? So the electronics have gone into ocean, and that electronics is actually fully of MEMS technology. Yeah. So you have everywhere, especially there is sound application and automotive electronics. Just a picture I want to show you of a accelerometer. This is how it looks when you see in the microscope. Okay. Also in aerospace, could be interesting things for mechatronics students. A lot of unmanned vehicles and also gyroscopes is one of the another major breakthrough in MEMS technology. Yeah, so you can browse through it at your free time. I just want to tell you that there's quite enormous applications have been already established with these technologies. Biomedical, this is what, even our research proposal assessment, what we are going to have is something going to be this. The next feature is, as I told you the other day, it's wearable electronics, where we bring the MEMS technology as a wearable electronics. Okay, just some of the well established already for the this blood pressure transfer, pressure, and also some biosensors are quite well established. Or wherever you want to transfuse medicines at a very controlled manner, where they have well established technology. Okay, some pictures I want to show here. Actually, there is a video here. You want me to play, or you want to see yourself later? Maybe you can see yourself later in your free time. So there's actually a wearable UV sensors these days, which you are also quite interested in in our lab. People can detect how much UV index today, then try to recover themselves from skin cancer and so on. So there's a enormous application in this field. Okay, let's now comes with serious technical aspect. So all the introduction is over now. We're going to little serious things. First thing is the principle of MEMS as a microsensor. Now, when I say now microsensors, what is there inside? We are going to focus. This picture, this block diagram shows. So we have first one is a micro sensing element, and you have an input signal to it. That is input signal. So this micro sensing element, the output of this is given to a transduction unit, and then this transduction unit has to be needs a power supply, and then output supply. So this is actually a overall block diagram that fits to any microsensors. Now let's go one by one. Input signal. So input signal could be, let me take an example of a human skin. Okay. So if you take our human skin, say for example, I'm going to pour a hot water here. So there is a temperature. There is a change in temperature. So input signal is a temperature now. Yeah. So this input signal could be any measurand. Okay. Let's know the word today. Measurand. I will be quite often use this. Measurand. At least that can be measured. It could be temperature, it could be pressure, it could be the glucose level in my sugar, it could be radiation level, or it could be presence of a gas or concentration of a gas. Okay, any sort of that we group all together as input signal. Okay, for example, when I say detection of gas, probably I mean the concentration of the gas. For example, in this room now, what happened is there is some, mostly our air atmosphere is of 78%, mostly is nitrogen, then around 20% is oxygen, and remaining is traces of carbon dioxide and carbon monoxide. Now we have pollution also, so those are also there. So majority of this is the air composition. Now for example, some way there is a leakage of a hydrogen gas, say for example. Now hydrogen, what happens is, people say that if it's beyond 3% in an atmosphere, that means 97% is air, 3% is hydrogen. Beyond this, if you cross, there will be a blast. Okay. say for example, in this kind of a situation, if say in the industry, it has to be always closely monitored. Okay, so we need a sensor. So the measurement here could be what? Hydrogen? No, measurement could be exactly hydrogen. No, percentage. More clear. We'll see who says. Concentration. Yes, hydrogen concentration. Yeah, concentration of hydrogen. So that's the measurement. This much concentration in this room. Say humidity. This is the percentage of relative humidity in this room. So those are all the measurements. That's the input signal. Then we have a microsensing element. So microsensing element is the one which is, here we can call it as a sensing medium. So in our case, this skin is actually could be an organic actually. It's actually made up of some organic material. Yeah, which is actually, and it is also connected with a lot of nerves, and it goes to the main processor brain. Yeah. So this skin is able to now react to that sudden change in temperature. It's actually some signals it is producing. This is sensing medium. Yeah. So likewise, in every sensor, there could be a sensing medium, which we call it as a micro-sensing element. Okay. Example. Any example you can give before I give in a real laboratories which you have come across. Say 3091 also. What? Light dependent resistors. That's the simplest one. What is there inside then? In that case, measurement is light wavelength. Okay. There should be some material inside. There is actually one version of doped silicon is there inside, which is actually good. Or there could be some semiconductor material which is actually changing its resistance. The resistance is changing with respect to the light measurement. Okay, so microsensing element is the sensing medium of a microsensor. Okay, which actually will mostly this microsensing element will exhibit a change in an electrical characteristics of the material. Can you name some of the electrical characteristics? If you know this now, your sensor masters now. Resistance, capacitance, or sometimes even inductance, or it could be a voltage or current. These are the major electrical characteristics. For example, the same LDR which we take example, I was saying on shining light you get a change in resistance. That means that material, what was inside as a sensing element, is changing its resistance, or in other words, inverse of resistance, conductivity. Okay, so in that case the conductivity is changing with respect to the light which was shined. Okay, so any of the electrical properties of that material will change. Just the change in the material properties. But the change in the material properties, say it's a resistance or capacitance, that will not give us, for example, we have say the same humidity sensor or the UV sensor, with what I told you, probably the wristband or which I was saying. At the end, finally, the end user wants to see in a mobile phone, oh, okay, this is the value today. They don't want to say, oh, this is the change in resistance for this. They don't want to go and search for what is the change in resistance. They will not refer to a book. Yeah? Right. So, at this point here, you only get the change in the electrical property. This has to be transduced to, an electrical signal in terms of voltage or current. Yeah? So that can be used to a microprocessor to read. Right? Then you do Bluetooth or cloud, you do whatever you want. So that transduction unit, which actually converts the change in electrical parameters to an electrical signal, we call it as a transduction unit. So this transduction unit, so somewhere it needs to get the electrical power also, so that it can do this job, is the power supply. So biggest challenge now is in all wearable devices. The current challenge is battery. Even our mobile phones, we need a battery to run the whole thing inside. So imagine now if I'm making wearable device, I have to carry a bulk battery and run. You can see that That's one of the major things. So whenever the sensor is there, probably you need to have. So somebody can think here how we can do something without any battery or very smaller battery structures. Yeah. Okay. So from that, from the transaction, we again will have the output in terms of electrical signal. So this is the micro sensor principle. How about the micro actuator? So actuator, now probably you can say it's sort of something inverse of what I was talking about. So we have now micro actuating element. So this time an actuator converts the electrical signal to mechanical action. So the electric signal, whatever you are going to give, we need a transduction unit. Any example of a transduction unit here in this context? Okay, before that, we'll come to that. So macro actuating element, what could be this? It could be a gear, or it could be a motor stator structure, or it could be a solenoid, okay? Or it could be a something like that, yeah? So this power supply has to again needs to transduce the signals to give a movement to this actuating element. So what transduction unit could be? What could be that? Some kind of a driver thing should be required to transduce these things. Right? The electrical signal has to be converted in some form that has to be provided to the microaching element to perform an action. So in both the cases we have a transduction unit which converts one form of the electrical, either voltage or current, to an electrical parameter, and then it is given to the either actuating or sensing element. An example here is, as I said, the stator or rotor, which is a typical here for species microactuating element. So overall, a microsystem can have both of this, that is both sensor and actuator, probably a common transduction signal unit or could be together. It's just a combination of these two. Right, so but overall, so this is just a sensor which is there lying on the table, but at the finally when the user wants to do it, as I said, now we want to have everything in our mobile, say for instance, or this we need to read the signal directly. So in that case, we need an interface of microprocessor, all these things. So that could be an overall big picture which can have all these signal conditioner and so on. Just I want to highlight how we evolved from a wafer to the final end. Okay, very important. This slide I always like to show this because some students they feel I am doing electrical engineering. Why the hell I am studying about H2O, C2O, H2O, O11, all these things? It's actually quite a lot of when you come to this particular point. It's probably you may not go so deeper into the knowledge of this kind of studies, but probably need to be aware of it. So it's actually more of an interdisciplinary work. So when in a MEMS company, there could be an electrical engineer who probably may be giving more inputs of the design, or probably more in terms of which for example in this case, the electrical engineer can actually design this power supply, electrical systems, all this integration of MEMS and CMOS, this kind of activities. Whereas a mechanical engineer can actually think of what dimension, how is the cantilever design, and so on. So every aspects are coming, it's a quite very interdisciplinary. So if an electrical engineer may not say that have to have idea of all these things to become an overall MEMS engineer. Right. So these are some references. So that's actually comes to end of lecture 1 only. Now lecture 2. Okay. This is my more interesting. Now, first we will see some examples of microsensors. So some typical types we are going to discuss here would be acoustic wave sensors, mechanical sensors, chemical sensors, and biological sensors, and so on, and some physical sensors. So the idea here is to make you to make aware of or make you to understand what is the principle. If I want to make say a pressure sensor or a humidity sensor, what would be the basic principle? Or if it is a chemical sensor, what is the basic principle behind that? That is the one we are going to learn. and how to think an idea to make them as devices is the motivation. So let's move on to, probably I thought of starting with the biomems. Okay, so after automotive electronics, as we saw in the applications, the another biggest market for this MEMS is the biomedical applications. Yeah, so there is a numerous number of updates that will happen in this field. So basically, people call this biomedical applications into one group called as biomems, and that can be classified into three types of devices. One is biosensors to identify, say, a chemical or a biological things, or bioinstruments and surgical tools, or some analytical systems to testing and diagnosis. I'll come one by one. So probably we will first start with okay, before going there. So there are some issues as well. Before we talk about the examples, there are some issues. Okay. So before people try to design the biomems products, probably they need to think of a few points in the mind. One is they need to clearly identify what is the functionality that was intended for these biomedical operations, or also they should also need to aware of what are the equipments or instruments are already available. For example, if I want to measure blood pressure, already we have some technique. Probably those days, now also they could have wrap around something and then they push the air inside and they see the mercury rising, yeah, something like that. But now, if you go to Sunwell, they put a clip for us and they directly take the reading. So previously it was there, probably the accuracy was an issue or something, or now you get too many readings just by putting this. Say you get the heartbeat and all these things. So there's an improvement there. So one has to know what is the present situation and then look forward. And compatibility with the biological system of patients, very important. So suppose I wanted to make a sensor. I feel that this sensor can detect AIDS and kill all the AIDS viruses. Say suppose I find like that. But that instrument or the chip, I say that I have to put inside my skin. Say for example, I find something like that. But it should be made sure that that is compatible with the human body. Yeah. Certain things will not be compatible. Because of you killing the virus, you may kill the whole person. Yeah? So one has to see whether it is compatible with the biological aspect. This is very important because silicon, if you see the generally, silicon wafers are the one from where the electronic chips are made. That has a good compatibility. Okay. Then controllability and mobility for such operations. How controllable it is. Okay, say for example in the laparoscopic surgery and so on. And okay, probably a bit boring. Let me go to the next one. So I would like to directly go to an example to highlight you. First sensor what we're going to discuss is a biomedical sensor. Example, I'm going to take a glucose sensor. Dr. Rama is showing some chemistry now. You are thinking so. The chemistry, what you know, is the same level the chemistry I also know. Okay? No different than you. I also studied only up to a certain level. Yeah? Okay, before we go to, let's refresh some of our chemistry knowledge. Anybody, can you tell me what is the symbol for a carbon? Hey, all are great in chemistry. All right. What is the symbol for hydrogen? H. Okay, good. Why do we write H2? Two atoms. Why we write H2? Why don't we write H? Huh? Now chemistry is problem. Eh? Very good. Somebody gave the answer just now. Not stable. Hydrogen has only one electron outside the valence electron. If you go for your grade 6, grade 7, you learn this. Okay. So what happens is they try to combine together and they get stable when you have complete 2 electrons in the outer valence electron. Yeah. So that's why you write H2. Okay. What do you mean by H2O2? H2O is water. Yeah. But when you write H2O2, what is that?
hydrogen peroxide.
Wow, hydrogen peroxide. Correct. How many of you know this? Okay. What is a hydrogen peroxide? Is what type of chemical is that? Is it a base or it is what is that?
Acidic.
It's an acid. Hydrogen peroxide is an acid. Yeah. Commonly, where we can find the hydrogen peroxide in our day-to-day cosmetics, if you use. Eh? First aid kit. I doubt. It is? Okay. I was not aware. One I aware is, if you notice, I actually have white hairs, but I color with black. Dark. It actually has H2O2. Yeah. H2O2, when you take out from bottle and you drop somewhere, after some time it just becomes water. It's an acid, but okay. H2O2 is a hydrogen peroxide. Okay, good. All are good with chemistry. You are on the same level of me. It's very nice to know. Then we'll proceed now. Okay, the intention of this sensor is to detect glucose in a blood sample. Okay. Now, the way how probably in the very ancient time, probably they might have taken the blood from the in a syringe. Probably they may need to do some laboratory experiments. It takes a time. Probably some students are already, I have some FIP students, they are trying to do some non-invasive thing, that's a different thing. But this one I am saying it could be invasive. You need to take the blood sample out if in that case. So I want a very tiny thing which can do that business. So here is the example. So this actually has a micro, say a micro tank. Huh? So this micro tank has a needle like this, like our mosquito beak. A tiny silicon microfluidic channel has been made. So once it has been pierced, due to some capillary effect, say the blood is flowing inside. So we fill a small, tiny drop of blood. Okay? I mean, this is the sample we have. We want to know what is the glucose in this. Any idea what is the chemical formula for glucose? I don't like anything memorizing, but these things I'm asking is to C6H12O6. Wow, very good.
Something C6 something I'm okay.
C6H22 C6H22O7. Okay, but whatever, O6 is actually a different form of sugars, sucrose, and all. There are many of the fructose and all the things. But generally, what I like to highlight here is some C, H, and O. There's a big number of H actually, 22 sort of thing, no? Large number of hydrogen molecules. Sorry, hydrogen atoms. Okay, so these many number of hydrogen atoms, these many number of oxygens, this many of carbon, they combine to form this sugar. Okay, so I want to see in my blood how much sugar I have. So that is actually depends upon how many number of these chemical compounds are, these chemicals are, right? Yeah. So one is you can see the hydrogen is of 22. So what this instrument does? So we are going to have two electrodes. One is called as platinum electrode. Another one is called AgCl electrode. This we call it as silver chloride electrode. Okay, this is not new again. You might have seen this before. Silver chloride electrode to take the ECG signals. Okay, you can see they stick something there. If you happen to see anytime somewhere, you can peel it and see there will be a jelly kind of thing. That's actually silver chloride electrode. It actually can transfuse the signals. Okay, so that's some sort of stuff is here. And this platinum is a metal. So, you know the platinum, quite expensive one, yeah. There's some electrodes, again they are in micro dimensions. Now what happened is, we are going to apply an electric potential to this, and we are also going to measure the current. Just exchange the values I and B, huh? It's wrong. So what we do is, inside this tank, we don't keep it empty. Before we collect the sample, we already store something called as polyvinyl alcohol solution. Okay. I also don't know polyvinyl alcohol. I know only Harpic in my house. So you're also the same condition. But what you should understand is, it has alcohol. Okay, alcohol is there. So what happens is, when glucose reacts with oxygen in the polyvinyl alcohol solution, so there are some oxygen in the polyvinyl alcohol solution, and there is hydrogen in the polyvinyl alcohol. The glucose reacts with this oxygen, and they form a new compound which is called a blah 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 blah, plus a hydrogen peroxide. Okay. What is interesting to see here is this hydrogen peroxide will dissociate. That's what I told you a while ago. You pour this hydrogen peroxide. It is you take out from the bottle. You pour out, it will actually dissociate. Okay. So until it is in bottle, it is reactive. It's an acid. It's an acid. Okay. So what happens is this hydrogen molecules, they start getting dissociated. The more the number of hydrogen molecules, so these are H plus positive ions. So the positive ions travel towards this negative. This is a cathode inside this. Okay, positive, negative attract. Boy, girl attract. Positive ions go towards the cathode. Now what happens? More the number of these positive ions, what will happen to this ammeter here? No. I have an ammeter here. What I can see through this ammeter? If more ions are moving towards, there is a flow of charges. So you will see a current reading. So this current is proportional to what? In this picture? H plus ions. How these H plus ions are related? Glucose. Yeah? So you can now see the glucose concentration is proportional to this. Hydrogen ions, the hydrogen ions is now actually creating a current circuit. So as far as electrical person is concerned, we will only now will focus on this. That's why I was saying the chemicals are not so good. But what we will have to grasp here is we look for some kind of this particular reaction for electrolytic reaction and see how we can get a change in current or a voltage. Yeah. So what is the microsensing element here? You see, if there is some reaction happens with, have I given the answer here? Okay, let's see this. This slide has skipped, right? Maybe you can now see. Microsensing element, a chemical that reacts with the sample. Which is that? Now we'll go to the picture. Which is the microsensing element? That polyvinyl alcohol solution. Okay, is a microsensing element. So that actually has this rich oxygen, which is actually going to dissociate this glucose. Sorry, this hydrogen peroxide. So the transduction units involves all these PT electrode and all these ammeters and all these things. The remaining part. Okay, so this is a typical example of a biomedical glucose sensor. So one can actually imagine this for many other applications as well. So the idea is this: you need to have something that reacts and can produce such thing. Any example you can think of? I'm also not able to think. Okay. Last minute. Okay, biosensor. I will stop after this. Biosensor is so fancy. So what I now told you is a different on biomedical sensor. Now there's a big difference. Now I'm going to talk about biosensor. This is the second type of biomaps. Biosensors, we use a transduction element or a sensor above which we will use a biomolecule as a sensing element. Example of some biomolecules. Too many new things, this one, lot of new, but all these things, I'm not telling anything very serious. It's already you might have heard in your school time, or just trying to recollect from that. Okay, so some of the, how do we get our food digested in our stomach? Any idea? Enzymes, very good. There is some secretion of enzymes that actually tries to digest the food materials what we eat. So enzyme is actually a biomolecule. Okay, it's an example of proteins. It's a biomolecule. So if such biomolecules are used as a sensing medium on a sensor and try to detect, okay, analyte is another term I'm going to use. Measurement is the one what I used to, which is measurable. Analyte is sort of again is a kind of measurement, such as, say for example, it could be anything. For example, I have a water tank in my house. So what happened is there is some algae formed inside it. There is some kind of toxicity happening, for instance. Or the pipe through which the water is coming, there is a lot of iron content. There is a rich iron content. I don't know. I drink every day, but I don't know how much iron is there inside. So what we can do is one can design a sensor. Okay, I'll talk about this sensor. There are some types, but the layer what I use is it could be a biomolecule that can change its activity. The biomolecule will change its activity for a presence of say analyte. For example, a concentration of iron or something, and that change is actually an electrical change. For example, the resistance changes, capacitance changes. That change can be read by the sensor. And we can read. Now, the difference between the earlier example sensor and this one is the sensing medium is a biomolecule. That's the difference. Okay, we will see more about this in the coming class. Okay, so I'll go slowly. I hope I'll make this interesting for you. Okay, see the lab also. Monday, right? Monday lab. I'll open the quiz. Sorry, I opened the lab. That